Hey guys, welcome back to another video in this series on Halide. I know it's been a minute. I haven't made any videos in the last month or so, and especially for this Halide series, it's been a long time. I've been busy with some work and I'm moving apartments, so hopefully from next month I'll be back on schedule and I have some exciting videos in the pipeline. So thanks for your patience. Today we will talk about multi-pipeline scheduling or multi-scheduling or however it's called or multi-stage scheduling. So in the previous video, we talked about single stage scheduling where you just have one operation and you kind of want to schedule it to make it as fast as possible. So today we look at some various techniques of multi-stage scheduling. Um, all the code that I will show today is basically from the tutorials on the Halide page, and this is just my commentary on it, or just explaining what's going on. All right, so here I have one of the research papers on Halide by the team, and I want to point out at this nice diagram. So we looked at these methods of single-staged scheduling. So, you can go row major, you can go column major, you can go tiled, you can vectorize, you can parallelize, and you can do parallel tiling. So these are the methods that you use for single stage. Now, for multi-stage, there are a couple more things that are added, but you will use again the single staged things or single stage schedules in conjunction with certain other API calls for multi-stage pipelines, and that's how you'll build up your multi-stage pipeline. So you still have to know the single stage procedures to build up on multi-stage. Here there is a simple example of let's say I take in an input and I need to blur it. So blurring operation is basically putting a grid on the image and averaging out the pixels. So this grid is a square grid. So you would think blur is a single stage operation, but then I can always break it up into two blurs. So first I can blur horizontally and then I can blur, horizontally and then vertically. So this splitting the blurring operation into two operations is um, makes it multi-schedule. So first I'll only do the horizontal blur and then I'll do the vertical blur. Now I kind of want to show you the two different ends of the spectrum. So let's say let's look at this compute route. So again, this is a call on your func on the Halide func compute route. So what it does is it waits for one stage to be completely done, and then it will move on to the next stage. So this is my input image. It will first completely compute the horizontal image, the horizontal blur, and then and only then it will move to the vertical, right? So that's one end of the spectrum. Let's look at the other end of the spectrum. In this other end of the spectrum, we have inline. So everything is completely inline. So what that means is this. So if I have to compute the final output, like the vertical blur, because that's the last operation. So to compute each of its pixels, we compute each of the blur horizontals relevant pixels, and then that goes back to compute the relevant pixels of the input image. So everything is completely inlined. Now, why did I say these are the two opposite ends of the spectrum? Because this inline would obviously be the fastest, right? Because you're not cache storing in anything, you are just using values as you get them. Um, the compute route, on the other hand, so let's stick to inline for a bit. However, inline would take a large time to compile because you have inline pretty much each operation. So that will take forever to compile. The compute route, on the other hand, wouldn't take long to compile, but then it's using excessive memory, and the vertical blur operation has to wait for the horizontal blur. So that's why these are like two opposite ends of the spectrum. Now, obviously, as with all good things, they are at the center. So center is where you'll find the best performance. And the reason why you kind of want to sit in the middle is in this inline operation, it's very redundant because if you look at this particular grid, that grid would be read multiple times for multiple pixels in BV. Like at least some of its pixels would be read multiple times by the pixel surrounding this one. So there's a lot of redundant operations. On the compute root side, you don't have redundant, but then it's a sequential process. So it's so you're sitting idle till BH is computed. However, you can compute some bits of BH and then use that to compute the BV values and so on. So this is how um, multi-stage scheduling would make this whole multi-stage process more efficient. And we will look into the different techniques that are present. All right, so let's jump in. Give me one sec. All right, so cool. Multi-stage scheduling in Halide. Now, I have the same image and it's the same kind of conversation. Now, here, the pseudocode is also presented here. So let me show you, or let me talk about what's going on here. Here, so basically this is again a repeat of what I've just mentioned. Here, this is the same blurring operation which has two schedules. This is compute root and this is inline. So in compute root, you have no redundant work because I completely compute the first stage and then I go to the next stage. However, it's hard to parallelize it, and then there is no locality. So I need to compute the entire image before moving to the next part. And in code, it looks like this. So I loop over both the y and x's, and then I do the blurring for the 3 pixels, and then I again, so this generates my BH, the horizontal blur, and then I move on to the same thing for the for the vertical blur. Um, right. Okay. And in inline, you have a lot of redundant work because of what I just mentioned. The same pixels are going to be read multiple times, maybe 9 times. Um, it's very hard to parallelize this. And however, it's super local because the values that you read are used right away. So, and this is how the inline code would look like. So I'm directly computing the V, and so I don't need an intermediate BH step. So I loop over all the pixels, the two for loops, and then BV is equal to um, all the 9 pixels, right, of the input. Now, the way they arranged it, think of it as each line representing one BH read. So this is for one BH, the second BH, and the third BH. And then you translate those BH back to the input. So this becomes directly, I go all the way back to the input image. That's how the two ends of the spectrum look like, right? So in this, so I kind of want to show you the same thing with a slightly different algorithm. Um, so our algorithm basically takes an input image, takes the sign of it. So depending so sign of the x and y. So for each x and y location, it'll compute its sign, and then we will compute the 4x4 grid average, and then finally just get the output. So now this 4x4 grid average, of course, can also be broken down into two steps, horizontal and vertical, but then we'll leave it as is. So take the input, compute the sign, take the average, and that's your output. Now, by default, Halide, in Halide, everything is inline by default. So that's important to know. So this is my algorithm. And the way well, the common terminology in Halide is to use the word producer and consumer. So in this one is the producer and this one is the consumer. So this produces some outputs and then this consumes it. It's just a terminology. In multi-stage pipelines, um, you could have like the parent of each stage is its producer and the child of each stage is its consumer. So just some terminology. So in step one, we compute the sign, and in step two, we compute the average. And then finally, you call the realize to JIT compile the code that tells it do it over a 4x4 box. The equivalent C code looks the following, where let me just bring it up. I loop over both the for loops, and then I directly compute the result, because remember, everything is inlined. So directly compute the sign, the average of the signs of the four values. So sign 1, sign 2, sign 3, sign 4, and the average, right? Because this is completely inlined. All right, now we'll take a slightly visual look at the same stuff again. So compute root. How does compute root work? What I said, what compute root does is it completes one stage first, and then it moves to the next stage. So all I have to tell Halide is make, so you have to call compute root on a particular stage. So for producer, I do producer dot compute root. That means it waits till produce the next stages that depend on producer would wait till producer is completely done. And then I call consumer dot realize, and this is how it looks. So notice the producer is first processed, and only then the consumer begins its job. All right, and the way it looks like this is it's sequential. So two for loops. First we compute the producer, and then another two for loops where we compute where we use the results of the producer, which is called produce stage, and then use it in. Okay, I hope that makes sense. All right. Um, Now, what we've noticed is in this is we have to wait for a long time for uh, we have to wait for a long time. As you can see in these in the GIF, we have to wait for a long time for the consumer to begin its computation, because first the producer computes everything. However, as you can notice, once the producer has read the first two lines, the consumer can start processing it, because the first line of the consumer only depends on the first two lines of the producer, because we're taking the average over four, remember. So that way, um, so let's say for the first row of my consumer, the whole of producer is not required. I only need the first two rows. And that's where we come to this whole compute root. What compute root does is it tells Halide to only compute or only compute a particular stage only when needed. And the way you specify only when needed is you specify what is the downstream function that handles what's needed, and which axis of the downstream are we um, interested in. So here, what are we telling? So y-axis goes down, x-axis goes towards the right. So the way we are telling it is compute the producer only at, so you right now you're computing it, you're not storing it in. So you just compute it, and you don't compute and store it. You don't compute and store it. So sorry, compute the producer only at the y-axis of the consumer. So as the consumer needs its y-axis, only compute it. So now if you look at this, I'll let the loop finish. You'll see the first two lines of the producer being computed, and then the consumer's first row gets computed. So now the consumer goes, and then the next two lines of the producer, and then the second line of the consumer. So this is how it's done. Now the equivalency code kind of looks like this. We compute the result matrix, and now I have an outer loop that goes over the y. Remember, y is the one that's going down, x is the one that's going to the right. It's like the row major read. Now I create a temporary variable, which is my producer storage, and I store the two rows of the producer in it. And then finally, in my results matrix, I loop over all the x's, and then the results, um, uh, store the results computing on this stored in this producer storage. So taking the average of the four grid values of the producer storage. So in a sense, what I'm doing is for each row of my consumer, I compute the relevant producer values and then use those immediately, and then that's it. So I get one row of my result. Now there is a slight redundant computation that's being done, and so if you look between the first and second rows of my consumer, the second row of the producer is being computed twice, right? Because it's a 4 by 4 grid, and then the middle row is being computed twice. So that's a bit of redundant computation that's still being performed. Now let's get rid of that. And the way we get rid of that is by the store root method. So what it does, store root, is instead of just computing it, now we store it as well. So that's the added advantage of, so that way we get rid of the redundant compute because we have already computed it once. So you don't need to compute it again. And one thing to note, in Halide, all these things can be chained. So, store root is called and then compute root is called. So, okay, let me tell you what's happening here. So producer.store root tells Halide or tells the producer to store whatever is computed. Now, whatever is computed at the consumer's X loop. So we've now changed it to the X axis of the consumer, and then we realize it. So let's see in this image, you would see um, for each producer's X, sorry, for each consumer's X, so for each blob of X, the producer does the four grid computations and then it moves to the next four and then the next four. And the overlapping grids are never computed. So first four, next two, next two, next two. Because I said X over here, that's why I am doing 4, 4, 4, 4. I'm going bit, 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 bit. If it was Y, then I would go straight, straight, straight. If it was Y, this would be kind of similar to inlining. Um, uh, because let's see, so if I replace this with Y, this would be almost equal to inlining. Right, yeah, because I would compute each. Okay, let me leave that for a bit. Let me first explain the whole X thing. Um, Again, let's step back. For each X, so X goes like this. So for each pixel in the consumer, I compute the relevant compute and store the relevant producers. So producers are 4. So for each bit, 4 are stored, and then we don't overlap the compute because it's already stored. The overlapping values are already stored. Now let me point you to the equivalency implementation. I get the result. I have now I create producer storage, which is now it's outside the loop. The reason why it's outside the loop is because we are storing it, and we're not storing the whole thing. We only store values that will be relevant for the x-axis of the compute. Okay, so that's why this thing is outside, and then the way this has been coded, it's kind of like a circular buffer where only the even though it's two, only one of the values will be updated depending on the logic um, because there is one row that is overlapping, right? So first I loop over the y's, and then I loop over the x's, and then the whole compute is within the x because of because um, we're computing at x. So for each x value, we do the producer storage computation. So this whole step is the producer storage computation, and then these if logics basically ensure that you only compute the non-overlapping um, scanline or non-overlapping pixels in the producer. And then once you have it, for the result, just take these values and then average them. and then move on to the next one, move on to the next one. So this is how this whole loop is done. Now let's see. If I replaced producer store root with y, then I would have to, so let's first look at what did compute at y did. So compute at y, it had an outer for loop, and then the relevant values were being computed like this, and then they were immediately being used. But then for y, we for each y, we had to compute the whole two lines of my producer. Hmm. Let's see. Give me a moment to think about it. Right. So, give me one sec. So if I had compute at with y on the y-axis, so what was happening is the computation, the producer storage is occurs within the for loop of y, not in the for loop of x. So now here, when I had compute out of x, the the uh, the producing bit is also within x. Now, if I just had a y, all that would change is this bit would remove out of my for loop and would go outside. I think that's the only change. I'm not sure about the performance wise, but anyway, that's all I wanted to share. Um, the next thing is tiling. Um, right. So in tiling, you divide your basically your for loops into an outer and internal for loop. So here my x and y are divided into x outer, y outer, x inner, and y inner 4 by 4. And when I compute, so here I make a call that computes. Remember, compute at does the computation. It doesn't permanently store the values. So unlike store root, which stores the values. So compute at will compute according to the x outer. So let's see. This should be 8 by 8 because now we are doing an 8 by 8. So for each X outer, now what's X outer? So X outer, the consumer has been divided into tiles. So X outer goes from 0 to 2 or 0, 0 and between 0 and 1. So this is X outer being 0, X outer being 1, X outer being 0, X outer being 1. So for each of these, it first computes the producer relevant to it, and then it does. So again, so first the producer relevant to that block gets computed, and then the consumer is done. Then the producer relevant to the next block, and then so on. Now for the code, again, so so for tiling, the codes are always first you have the outer loop, and then inner. So for y outer and then x outer. So now within the x outer, we store our producer storage. So here we compute the producer bit that we need for storing the relevant consumer computation. And then we have the for the y inner and x inner, and then we use the producer storage to compute the result. So that's how tiling helps. And now you can use all of this to do something crazy. So now in a big image, this is how you can make use of all these things that we kind of learned to just go ham. So let's see what's happening here. So let's go step by step. First of all, what I have here is we split the consumer into an outer and inner with 16. Oh, the video doesn't work. With 16 scan lines. So for each of the outer y, so in this axis we split it into chunks of 16. So each of these scan lines are 16. And then we parallelize the outer ones. So notice how for the consumer, like just for now, because we are doing consumer dot, just look at the consumer. So notice how four of these are going together, and then another four. And each of these four threads would do 16 scan lines. And so that's why we've parallelized the outer loops. So that's so the four going together is a result of the parallelization, and the other, all these lines going together is a result of the inner split and Tyler kind of equivalent. Then we vectorize the x dimension. So x dimension is the one that goes like this. So take four values at a time. So I know it's kind of hard to read, but then if I pause at an instant, you can see four values are being read in one go. So read four at a time. So you vectorize by four. All this while we are only looking at the consumer. Now let's look at producer. Producer.store consumer YO. So what it does is it stores producers per strip computation. Now this block is a strip because this block has the same yi outer, but its y inners goes from 0 to 16. So for each block, save the values. So save the producer values. So let's see. Um, right. So okay. We are going to save the values, but then let me hold off explaining this bit. Let me add in the next two bits as well, and then I think we can completely explain the whole thing. Um, so, so that's what you're storing at. Now, how am I computing the producer? So the producer is being computed at the inner values. So producer, I would compute at the inner values. So for each of these scan lines, do the relevant computation for the producer. And then you can also vectorize the x-axis of the producer. So what's happening is for each consumer's line, I compute only the relevant producer, and then I store all the um, outer strips. The reason why I will store all the outer strips is because, so let's say we almost reached this part of the computation. In this part, there would be these overlapping lines, right? So for this scan line, it would use things from the top and bottom, the producers from the top and bottom. So you don't want to um, do that redundant computation, and that's why we have stored according to y outer. And then the vectorization bit is simple. So these things require, a bit of mental. You have to like think about. So I hope the equivalent C lines made it a bit easier to understand like, what's going on. But then when you look at this, you have to just um, do a bit of trial and error and then try to go step by step. So typically it's best to go from output to input. So we are going from consumer to producer. So if you go step by step, it kind of makes sense. What you want. You want to do the only the relevant compute. You don't want to do any irrelevant computation, and that's why you store at and compute at. So this is how this is basically what I wanted to talk about in multi-stage scheduling. Now, if you want to play around with the code, let me point you to where the code lives. If you go to the Halide webpage, go to tutorials, and if you go to this on the left, if you go to multi-stage pipeline, and there's another scheduling multi-stage pipelines, this contains the code that you will need to play with um, with all this. All right, I hope this was useful, and I hope I didn't make any errors somewhere because this is a bit confusing. But all right, I will see you guys next time, and keep a lookout for the PyTorch videos. And then I have some more cool and fun deep learning stuff also coming out. See you guys next time. Bye.